Let's look at an example of how we can use the effectiveness NTU method to define the size of a heat exchanger. We have a counter flow double pipe heat exchanger, and we plan to use it to heat the water from 20 to 80 degrees C at the rate of 1.2 kilogram per second. And the heating is going to be accomplished by geothermal water. So this heat exchanger is close to a geothermal well that the water is coming out at 160 at the mass flow rate of 2 kilogram per second. Now, the inner tube is thin wall and has a diameter of 1.5 centimeter. The overall heat transfer coefficient is given by 640 watt per meter square Kelvin. Using the effectiveness NTU method, determine the length of the heat exchanger required to achieve the desired heating. So we are going to heat the water from 20 to 80 at this rate, 1.2, with the geothermal water, some sort of brine, which has a temperature of 160, and it comes at the rate of 2 kilogram per second. So I can make a quick schematic of what we have here. So we have a double pipe heat exchanger, and it's a counter current flow. I'm not really doing a good job in plotting that, but let's say this is okay. So this is the outer pipe, and this is the inner pipe, and we know cold water gets in, goes out. So this is cold water at 20 degrees C and rate of 1.2 kg per second, and we are planning to have this cold water heat up to 80 degrees C, and then we have a hot stream here. This is the hot geothermal brine, which is water, and it comes with a rate of 2 kg per second and 100 degrees C, and it goes out. We don't have the temperature of outlet. Okay, so these are really what we know for this problem. I don't want to really write down the temperatures here. The other things that we know, that's the diameter. Pipe diameter is 1.5 centimeter. The overall heat transfer is 640 watt per meter square Kelvin. And okay, I'm using a specific heat capacities for respective temperatures. So let's say CPNC is 400, 180 kg per joule per kilogram Kelvin, and CPNH is 400,310 joule per kilogram Kelvin. Okay. In terms of assumptions, let's assume we have a steady operations. Yeah. Steady operation. What this means is we have a steady state conditions, like the temperature is not supposed to change with time along the heat exchanger. So we have a steady operations and negligible heat loss to surrounding. So it's a very well insulated type heat exchanger. And the other thing is constant properties. And no fouling. So really, there is no deposit on the pipe inside or outside the pipe that could add resistance to the heat transfer. So now knowing all these things in effectiveness NTU method, the first things that we do is we define the heat capacity rates. Okay, so heat capacity rates for the hot stream is M dot H. CPNH, which is 2 times 4130, no, 431. and is 8620 watt per Kelvin. Cc, the heat capacity rates for the cold stream is m.c cpnc, which is 1.2 times 4180, going to be 5020 watt per Kelvin. So these are the heat capacity rates. Now, knowing these two, we can determine C mean. So here, the next step, that's the first step, second step. Don't know whether I'm going to continue numbering them, but the C mean here, we pick the lower value. So it's going to be Cc for the cold stream, 5020 watt per Kelvin. Okay, so now we know that one. We define the capacity ratio, C min over C max, which is 520.8620, and it's going to be 0.582. Okay, so this is the capacity ratio. Then we can define the maximum heat transfer rate, maximum possible heat transfer rate, which will be Q max is C min THI minus the inlet temperature for the cold stream. So 5020. Inlet for the hot stream was 160 and the cold stream is 20. So we would get 702.8 watt on a kilowatt. Okay, so this is going to be the maximum possible heat transfer rate. Now we can find the actual one, the actual heat transfer rate. Q is m dot c cpnc tc out minus tcn in, which will be 1.2 4180 80 minus 20. So we will get 301.0 kilowatt. Now, please note that here, since I have the inlet and outlet temperature of cold stream, I can find the actual heat transfer rate, and then I can find effectiveness. So depends on the problem. Either we don't know the effectiveness or we don't know the outlet temperature. So we go, and we know other things. We know the surface area. Then we can define NTU, and from there we find out epsilon that I will go through another example. But for this case, what we don't know is the surface area. We don't know the area that is needed, and that's what we have been asked here to determine. So knowing that, what we need is I get the actual from the known and everything, and then I can find out effectiveness. So epsilon is going to be Q over Q max. So what we are going to get is 301.702.8. And the ratio would be 4:8. Okay. Now we can use in the last part, we can use correlations, relationship that we have, not correlations, the relationship that we have between epsilon and NTU, or the chart to find out NTU for this heat exchanger. Now for countercurrent double pipe, there is a table that gives you NTU based on C and epsilon. So it's going to be 1 over C minus 1, natural log of epsilon minus 1, epsilon C minus 1. And if we do replace the number, it's going to be 0.582 minus 1, natural log of 0.428 minus 1, 582 times 428. 28 minus 1. So if you do the math, NTU is going to be 651. And we know that this NTU is UA over semi-nu. So from here, I can find out area that is needed is going to be NTU times C mean divided by U, overall heat transfer coefficient. So if I do the replacement 0.651, the minimum is 5020 divided by 640. So the required area would be 5.11 meters square, which is a large number. Now, another assumptions that I didn't put here is, it says here actually, it's a very thin wall, okay? So thin walled tube, what does that mean is di is almost equal to do, which have been given here. So having that one, I can say A is IDL and L is going to be 5.11, 3, skip it as I, and it's going to be 0.01. So it's giving us 108 meter. So if we really want to heat it up, the water from 20 to 80 degrees at the rate that we have, we would need a double pipe heat exchanger of over 100 meters. Now, I'm just going to add this one as a note, actually. Having L over 100 meters is definitely impractical. It would be super expensive, really practical, even making that and making that space and insulating that one. So alternatively, we should use other type of heat exchangers. It could be like a plate heat exchanger, or we can have a other types of heat exchanger, such as multipass. Shell and tube heat exchanger, or it could be like plate heat exchanger. Now, for this particular problem, as I mentioned, we know the inlet and outlet temperature for the cold stream. So really finding the heat flow rate was not really difficult. So we could get the actual heat flow rate, and then we could get the effectiveness here, but the unknown was NTU or area. Now, for this specific problem, we can use LMTD without needing to do any iteration. So that would fit here. And I'm asking you to do the LMTD, the delta T, the log mean temperature difference method, to solve these problems and compare the lengths that you're going to get from that technique to this one.